and welcome to episode 0 of Kradle Explained. Today I'll show how I determined the precise timing for eclipses in Kerbal Space Program, so I could get footage to use in my 2001 A Space Odyssey homage shown here and in the intro to my KSP career playthrough series, Out of the Kradle. Kradle Explained is meant to serve as a companion series to Out of the Kradle, in which I explain subjects relevant to my activities in the game. I expect the range of topics covered to be decently wide, and really just be decided by whatever I think is worth talking about. These videos should stand alone without having viewed the corresponding Out of the Kradle episode, but will probably be more interesting if you have. With that said, let's jump into it. We'll start by describing an eclipse intuitively. In the Kerbin-Mun-Kerbol system, two types of eclipses can occur. Kerbolar, in which our line of sight to the sun from the surface of Kerbin is obscured by the moon, and Munar, in which our line of sight to the sun from the surface of the moon is obscured by Kerbin. Let's use this description as the basis of a more precise, useful definition. We'll draw a pair of lines from the center of Kerbin to the centers of the moon and to Kerbal. We can now define an eclipse according to the relationship between the directions of these lines. Specifically, an eclipse occurs when these lines are parallel to each other. The eclipse will be Kerbolar when they point in the same direction, and Munar when they are opposite. The relative angle between these lines will be 0 during a Kerbolar eclipse and 180 degrees during a Munar eclipse. Because they have directions and magnitudes which are equivalent to the center-to-center distances between Kerbin and the body in question, we can refer to these lines as vectors, which we'll call our moon and our Kerbal. Of course, to express the directions of these vectors, we'll need for them to exist in a coordinate system, and so our next step will be to define a coordinate system suitable for our purposes. First, we'll select the center of Kerbin to be the origin of our coordinate system. Now consider the location of the Kerbal Space Center on Kerbin's surface at game time 0, or t0, which we'll call the epoch. We can draw a vector big R from the center of Kerbin to this point on the surface. Now we can define the first axis of the coordinate system, which we'll call I. I points from the origin through the position of the KSC at the epoch, and so it has the same direction as big R at the epoch. Next we'll define the fundamental plane as being coincident with Kerbin's equator, bisecting Kerbin at 0 degrees latitude, and since the KSC is on the equator, the I-axis lies in the fundamental plane. Now we'll define our second axis, J, as rotated positive 90 degrees from I in the fundamental plane. I've chosen a right-handed coordinate system, and so a positive rotation is counterclockwise if we view these axes from the top down. Finally, we'll define the last axis, K, as the vector cross product of I and J, which points up and perpendicular from the fundamental plane. Note that because we selected I to point through the KSC only at the epoch and at no other time, our coordinate axes will remain fixed in their orientation as the surface of Kerbin rotates underneath them. Additionally, the system's origin will always be at the center of Kerbin, moving with the planet as it moves through space while the axes retain their orientation. Because of this, the coordinate system has the property of being apparently unmoving with respect to Kerbin, which is referred to as being inertial. So we'll dub this coordinate system the Kerbin-centric inertial coordinate system, or KCI for short. Now let's reintroduce the vectors our moon and our Kerbal in the KCI system. Here's our moon, and with it we've defined a new angle, theta moon, which is the angle between the I-axis and our moon. We can do the same for our Kerbal and theta Kerbal. We now describe the angle between our moon and our Kerbal as the difference between theta moon and theta Kerbal, which is of course pi radians, or 180 degrees, for a Munar eclipse, and 0 for a Kerbolar eclipse. Let's proceed to analyze the motion of these vectors and angles so that we can predict when they'll align in such a way that an eclipse occurs. Because the moon's orbit has 0 degrees of inclination, that is to say the moon's orbit is in the fundamental plane of our KCI system, we can view the Kerbin-Mun system from top down in the IJ plane. Here we have the moon portrayed at its position at the epoch, with our moon and theta moon at the same time. Since the moon's orbit is perfectly circular, we can write that from its initial position, theta moon will change at a constant rate of 2 pi radians divided by t moon, which is the moon's orbital period, or the amount of time it takes for it to complete one full revolution around Kerbin. This proportion expresses the moon's orbital rate because it encodes the number of radians, or the amount of the moon's orbit that it moves through, per the unit of time that we've expressed the moon's orbital period in t moon. With these parameters, we can create an equation of motion for the moon by multiplying any time t with the moon's orbital rate, and adding theta moon at the epoch. Hence, we can write theta moon as a function of time, and we note that it depends on the value of theta moon at t0, and that this equation only works for a body in a perfectly circular, uninclined orbit. If we know theta moon at any given time, we can write our moon as shown. We use column vector notation here to express our moon, in which the quantity in each row represents the I, j, and k values of the vector respectively. Here the scalar our moon is the magnitude of the vector, which, since the moon's orbit is perfectly circular, will always be its orbit's semi-major axis. Since Kerbin's orbit around Kerbal is also perfectly circular and uninclined, we can repeat the same analysis in the Kerbin-Kerbol system, which is portrayed here again with theta and r at the epoch. Of course, T Kerbin is the period of Kerbin around Kerbal, which is 1 game time year. Revisiting our definition of an eclipse, we have that the angle between the moon and Kerbal is equal to pi radians during a lunar eclipse and 0 for a Kerbolar eclipse. For reasons that'll shortly become clear, it's convenient to take the cosine of this difference, which for lunar and Kerbolar eclipses yields values of -1 or 1, respectively, and values between -1 or 1 for all other times. When we expand these angles to their expressions as functions of time, as shown here, we get a sort of eclipse function, which has a periodic character due to the fact that we're taking the cosine. This is useful because the properties of the sine and cosine functions allow us to extract the frequency, and thus the period of eclipse occurrences of a particular type. We see that the period of eclipse occurrence depends on the periods of the moon and Kerbin, which are known quantities, and is equal to 6 days, 3 hours, 11 minutes, and 55 seconds. Analyzing this equation and identifying values at or near -1 or 1 is quite simple, except that if you've been paying attention, you'll notice that I failed to include key pieces of information. Our equations of motion and eclipse function depend on the values of theta moon and theta Kerbal at the epoch, which are missing. The moon and Kerbin's perfectly circular and uninclined orbits that allowed us to conveniently simplify our analysis also causes their classical orbital elements to be undefined, making them unavailable to us here. Since we've defined these angles in a coordinate system entirely of our own making, the game obviously doesn't provide us with this information either. Short of options, I had to resort to a much more manual way of obtaining these angles. I decided that my best bet for getting theta moon and theta Kerbal at the epoch was to take optical measurements of the positions of these bodies from the Kerbal Space Center and use a process which I'll explain shortly to compute these angles. To this end, I constructed a crude telescope using a camera part from the WholeCam VDS Continued mod and made a reticle from extendable antennas. The assembly is mounted on a hinge and swiveling rotor, whose positions I bound to the pitch and roll control axes respectively. With this, I could steer the telescope's line of sight somewhat precisely and directly view the moon and Kerbal. I positioned the telescope slightly north of the KSC at 0 degrees latitude. This position is the notional location of the KSC at the epoch that I used to define the KCI coordinate system. For both the moon and Kerbal, I pointed the telescope at the centers of each body as closely as I could and recorded the following 3 pieces of information: the body's compass bearing from our telescope, which we'll call the azimuth, its angle above the horizon, which we'll call elevation, and the time at which the observation was recorded. Using these data, we can determine small r for the moon and Kerbal at some point past the epoch, from which we can use the equations of motion we've created to determine theta moon and theta Kerbal at the epoch. Let's now study an example observation to see how we can develop a technique for determining theta. We'll represent the observation as a line of sight from the telescope to the sighted object with the vector ρ, and also draw the familiar big R vector to the KSC. We measured the object's azimuth, which in the cases of the moon and Kerbal will always either be east, 90 degrees, or west, 270 degrees. We also measured the object's elevation, or the angle between ρ and the local horizon. Using these data, plus the location of the KSC at the time the observation was taken, we can get vector small r. If we have small r, we can calculate theta at the time the observation was taken, and using our equations of motion, find theta at the epoch. As in our determining the equations of motion, we can again simplify our analysis for the moon and Kerbal by viewing the system from top down in the IJ plane. Let's momentarily hide these axes to focus on the problem of getting small r. We again have our ρ vector, characterized by its azimuth and elevation angle, and small r. Together with big R, these form a triangle. We'll define the interior angle A, which is simply pi halves radians, or 90 degrees, plus the elevation angle. We'll next define the interior angle B, which we obtain using the law of sines. Finally, we get angle C, which from the properties of a triangle is simply pi radians, or 180 degrees, minus A and B. Angle C gives us small r in relation to big R, but we need small r in relation to the I-axis, since this is the definition of the angle theta. This is quite simple to find if we know the position of the KSC, or in other words, the angle between our big R vector and the I-axis, which is called theta KSC. We can write this angle as the product of omega, which is the rate of rotation of Kerbin's surface, and t, which is the in-game time at which our line-of-sight observation of the body in question was taken. Omega is simple to determine by dividing 2 pi radians by the rotational period of Kerbin's surface. It's important to briefly note that an intuitive understanding of planetary rotation would lead us to associate that period with the length of an in-game day, which is 6 hours. In the astronomical sense, one game day can be interpreted as the length of time it takes for Kerbin to rotate until the sun reaches the same point in the sky as when we last observed it. We refer to this as a solar day. But of course, Kerbin itself moves along its orbit around the sun while its surface rotates, and as this diagram shows, which is in no way to scale, a complete solar day takes slightly more than one complete rotation of Kerbin's surface. So we instead associate Omega with what's called a sidereal day, which refers to the length of time for Kerbin's surface to complete one rotation, and is, of course, slightly shorter than a solar day. Specifically, a Kerbin sidereal day is 50.6 seconds less than an in-game solar day of 6 hours. So, by computing theta KSC and subtracting angle C, we can get theta at the time of observation for the body in question. But there's one more nuance to be addressed. We've built our case using a theoretical sighting with a west bearing. What if the object bears east when being observed? It should be clear that instead of subtracting angle C, here we must add it to theta KSC. Using this technique for the Moon and Kerbal, we can get small r in relation to the position of the KSC, and then get theta at the time that the observation was taken. For the Moon and Kerbal, let's call these observation times T1 and T2 respectively. With the angles theta Moon and theta Kerbal known at times T1 and T2 respectively, we can rearrange our equations of motion to essentially rewind the paths of the Moon and Kerbal to get theta Moon and theta Kerbal at the epoch. This provides us with all the information we need to solve the eclipse problem and determine the times at which kerbolar and lunar eclipses will occur. At this point, all that was left was to get a solution, so I wrote an octave script that found points in the eclipse function with values at or near 1 or -1, determined their times in-game, and compiled a table listing relevant forecast data. Any good model should be rigorously validated for accuracy, and having done all of this math to solve our eclipse problem, I was very interested to see the degree of precision that this methodology could achieve. And of course, this could easily be done with the telescope vehicle I built for taking observations. This time, we'll be using it to visually verify the predicted times and elevation angles of eclipses that my model forecasts. Obviously, we can't verify a lunar eclipse this way, because the Moon and Kerbal are opposite each other, but we can verify kerbolar eclipses with one observation when the Moon crosses the center of Kerbal. To provide these predictions for testing, however, we need to revisit a nuance of how we mathematically defined an eclipse at the start of this video. Recall that we defined an eclipse as any time at which our Moon and our Kerbal pointed in the opposite or same direction, as is shown here in the case of a kerbolar eclipse. We'll be observing such a kerbolar eclipse from the KSC, shown here, with the familiar vector big R pointing from Kerbin's center to the KSC's location on the surface. We can use vector subtraction of big R from small r for the Moon or Kerbal to obtain the line of sight vector ρ from the KSC to either body in question. And in drawing these vectors, you'll notice that when the Moon and Kerbal meet our definition of an eclipse, the line of sight vectors are out of alignment, meaning that from our view at the KSC in this nominal eclipse, the Moon will appear slightly below the Sun at our predicted time of eclipse. There's nothing wrong with this per se, but validating the model would require taking observations of the Moon and Kerbal simultaneously while at different positions, which would be needlessly complex. In fact, we can do a little more math to figure out when the Moon will cross Kerbal's center from our telescope's perspective at the KSC, allowing us to verify the model with only one measurement. Rho Moon and Rho Kerbal differ by an angle beta, which can be computed using a rearrangement of the definition of the dot product between these vectors. With knowledge of the positions of the Moon and Kerbal for any time, it's easy to find a time at which beta is equal to 0, or cosine beta is equal to 1. So we'll take our validation observations at the times when Rho Moon and Rho Kerbal are in agreement. I've chosen 2 predicted eclipses that are visible from the KSC to validate the model, and as you can see from each observation, our predictions are good to within a few tenths of a degree in a few seconds. I consider this a decent success. Now the only thing to do is get a camera in the right place at the right time behind the Moon and let the magic happen. This has been Orbital Green Friend presenting Episode 0 of Kradle Explained. I hope you enjoyed and that you'll join me next time. Till then.